Welcome to my presentation, The Early Spine and Movements, How It Evolved and Came to Be by me based on my paper. Just give me a moment here. There we go. So when we think of what holds us together, one of the things that should come to mind first is the spine. It may not be important as the atoms that we have in our body. However, our spines are what hold us up. And one of the things I want to talk to you guys about is the difference that we see between land and terrestrial creatures, or excuse me, aquatic and terrestrial creatures. That's water and land. In fish, we most often see this kind of middle body plan is what I'm going to call it, where we have the spine in the middle or the center of its body, whereas in this dog, for example, we have the spine that's more towards the top of its body. And one of the things that's interesting is that we all know that life comes from water. So at some point, how did we get this change? And that is what we're going to be talking about today. So we have to go to the very beginning to talk about this. The first quote unquote fish is called the Hycoichthyes. And the reason why I bring it up is because, like I said, it is the first fish. It had pretty much all the indicators of an aquatic vertebrate, which is a creature with a backbone or a spine on the inside. Some of the features were that it had dorsal and ventral fins, a pericardic cavity, W-shaped myomeres, which is essentially critical to being a fish, gill pouches with branchial artery arches, and a actual notochord. It was really primitive in that it had multiple repeated gonads and a lack of a skull. However, because it was the first fish, does have an honorable mention, and it did, and a notochord is like a early primitive spine. The really big creature I want to emphasize here that has this photo right here is the Pikaia gracilens. It was found in the Burgess Shale around the time of the Cambrian explosion. At the time, most creatures were crustaceans, where they were more of invertebrates, where, ancestors of the crab, the lobster, it's where we see trilobites or cnapsids. But the Pikaia gracilens was a little bit different in that it's similar to eels or aquatic worms that we see today. It did have a primitive notochord, um, and it also had bilateral symmetry and a clear distinction of head from tail, which is really important because most animals that are vertebrates have both these characteristics. Radial symmetry with no head and tail distinction isn't really made for movement. It's more of like a sponge lifestyle where you don't move very much. This would have been an advantage at the time because it would have moved similar to the eels we see today. It could swim with direction, move rapidly, and that would help escape potential predators, especially since it was one of the only creatures at this time that had these features. Um, One thing to mention is that all fish across the board are vertebrates, but specifically the one we'll be focusing on is a subclass, which I'm going to butcher the name, Osteichthyes. And they're bony fish, that's the fish that we saw earlier with the spine and its bodies, but all land mammals come from that class. Moving from water to land, we have the tiktaalik, which is the first recognized tetrapod. But usually there's a reason that would push an animal towards something. Animals are not by nature curious in just a simple, innocent way. So there's not a specific method or thing that actively pushed it, but a couple hypotheses was that it was a way to escape predators because most predators couldn't do what the tiktaalik could. Maybe there was extra food on land, which meant really no competition. And maybe they'd have access to prey and smaller invertebrates that were in the shallows. Regardless of the reason, the tiktaalik came onto land and back onto water on a daily basis, not just an every now and then sort of thing, which happens to be that amphibious lifestyle that we're looking for. We also see in this kind of skeleton right here, as well as the recreation, is that we see it has a little bit of a different fin. It's more for pushing itself up and onto land instead of just swimming. Not only that, but we see kind of the spine. It has more of that middle back area, which is really needed for that up and down motion. Bony fish usually have that side to side motion. So as time went on with the tiktaalik, we see a lot of changes. It would have had to had the skin would have had to have changed for it to be truly terrestrial. It would have had to change its physical structure because now you have to figure out the weight of being on land. Not only that, but the tail would probably have to shrink because you wouldn't really need it as like a fin to swim in the water, but it wouldn't shrink so much to cause a weight imbalance. So from here, we have a return to water, and we have a couple of main stages. We're really just going to go through 1 through 3. because these are the ones that we don't really have much knowledge about. Stage 4 are things that we often know most about since many whales are still around today. But I'll briefly mention one or two of them. So in stage 1, we have Pakicetus, and this was really a semi-aquatic animal, not a amphibious, which is really important to distinct. And you can clearly see it's not a whale. It has fur, it has ears, it has back limbs. Most of the time, it really just swam to feed on planktivorous or planktivorous animals and maybe some bigger fish that resided in the shallows. And its ancestors would continually spend more and more time in the water. One thing is that it does have transitional hearing. In aquatic creatures, a bone called the tympanic bulla and the malleus are fused as a way to hear underwater better. In terrestrial creatures, they aren't fused at all, but in the Pakicetus, it's partially fused, showing that it's kind of we're getting into the water again. It also had a shorter ilium, which is a broad bone that forms the upper half of the pelvis, which indicates a semi-aquatic life. Moving on to stage 2, we have Ambuloceus and Mycetus. Mycetus is this bottom skeleton right here. They're both in the same class of that, still more land than aquatic. However, they are starting to get into that transitional period. Ambulocetus had more powerful elbow extensions that later species would have had and more flexible joints than previous versions. Both of them had advanced hearing and swim with its feet, but came back on land to give live birth. Most of their swimming ability would come from the spine, specifically with its muscles. It would swim by moving its spine up and down, moved on land with the use of its forelimbs. The third stage we see in the Dorudon, which is this top diagram here. We see pretty much a total loss of these back limbs. They had short necks, forearms that were flipper shaped, and a definitely more streamlined body. This is more of an aquatic all the time kind of thing. There is, however, also another species in this called the Basilosaurus, which was essentially the cousin of the Dorudon. They were competitors, and the Basilosaurus was a little bit bigger. So in terms of advantages, the Basilosaurus definitely had that. With the fourth stage, the only one I could give an honorable mention to is the Lanocetus, which was essentially just a really early toothed whale. But overall, from that land back to water transition, a lot of things would have to happen. The toes would need to fuse, or tissue would need to envelop the toes in order to create a fin. The limbs, which were originally meant for land, would need to change with the arm bone shortening, while the quote-unquote fingers would lengthen. The loss of back limbs, though in modern whales, there are sometimes vestigial structures where a pelvis once existed. The muscles and bones connected to the spine would have to change because we're switching from holding our weight up to swimming in water. Movement from water whales nowadays heavily relies on the spine and muscles, considering most of it is skeleton, and they still have the up and down motion that shows that terrestrial ancestry. So it is kind of amazing that through so much physical change, there's little actual change to the spine. However, let's talk a little bit about the differences, because each spine is a little bit different for their environments, despite the fact they both live a fully aquatic life now. In the fish spine that's centered in the middle, we see that it's more streamlined for water. It has that vertical side-to-side motion versus whales that have the horizontal up and down with its fluke. And that up and down, it's more horizontal, like almost a wave almost, if you've ever seen a whale swim, which was originally good for pushing off of the ground and creating an opposite ground reaction force. Meanwhile, fishes are kind of built for slicing through water. But both of them have different uses for the tails and spines. For instance, whales sometimes use their tails to attack prey. They've been known to throw seals out of the water to confuse them. Some killer whales, there was a study done that were reported to swim around and essentially slap herring by stunning them while completely submerged with their flukes. Thresher sharks all sharks technically are fish, and thresher sharks are no exception. They actually use their tail to slap and incapacitate sardines at any time and were found to eat more than one sardine at a time, which suggested that the tail slapping is an effective foraging strategy for hunting school prey like herons or sardines. Sharks are a little bit tricky because they do have a cartilage skeleton. However, they are still fish. And so, in conclusion, the spine has played a clear and pivotal key role in how vertebrates have lived and survived in both the past and the present. So we've seen multiple species and how they've used it and how they've gone through multiple changes, and yet the spine itself hasn't changed that much. Even humans, the spine itself hasn't changed. We've simply adapted to carrying the weight and the stress that we have. But without this progression of changes, I mean, where would we be at today? Without the tectonic's movement to land, the changing of pressures, weights, and other environmental pressures, like where would the world be at? In the end, we'll never know, but without these changes, we and all other creatures will not be able to live as we do now. That's where I end. Here are my references. And with that, thank you for listening. If I can actually turn this off. Thank you for listening.